Okay, so I'll take your doubts from the assignments. So at the end of the class. Okay. So now let us start with this new topic, that is here work for energy. So before going to this work for energy here, let us just recall the definitions of each individual term here, right? Starting with the energy. So how do you define the energy? How do we define energy? Yes. How do we define energy? Huh? Ability to do work. I don't know what is work. I'm starting with energy. You are giving another unknown word. Unknown word. Ability to do work is like maybe I think sixth or seventh class definition, right? So, but now you have completed your 12th also, correct? Yes. Yeah. So actually, there is a very interesting uh, a look which we can have at the energy. I define energy as it is also a mass actually. There is no, fundamentally, there is no difference between mass and energy. The reason is that, let us say if a mass, I mean like if it is taking a form, then you can say that it is mass, right? And a formless mass, I define it as an energy. What is that? A formless mass, I define it as energy. And that's where your this Einstein's mass energy equivalence comes into the picture. Got the point, right? Where I think in your chemistry also you study, right? That some of the energy, or there is a mass defect which comes into the in your chemical reactions, right? Even in our physics also we study that in the modern physics chapter, right? So we define a term called mass defect. What does it mean? What does it mean? I mean, mass converted into energy, right? Is it possible that energy also gets sometimes converted into mass? Yes, it is possible, right? Yes, it is possible, right? But then since we don't see that in a large scale, since we don't see that in a very large scale, so we assume that energy and mass are two completely different things. Got the point, right? So now, but when it comes into the practical cases over here, let us say I take two bodies over here. Okay, there is a body, one particular body. Uh, Same number of like molecules are present in this one, and the same number of molecules and same type of molecules are present in this one as well. That means like physically both of them are having the same rest mass, right? And let us say that it started moving with some velocity v. It started moving with some velocity v here. Then a rest mass of this and a mass of this object are not the same now. Try to understand this. Rest mass of this and mass of this one are actually not same, but then in our mechanics we consider them to be same. Clear? In our mechanics we consider them to be same. Now, and since your energy is available in different forms, right? So we define like each energy is defined differently, right? So let us say if you go for the kinetic energy, how is it defined? How is it defined? So it is a form of energy. So by virtue of the motion of the body, right? Let us say you go for the heat energy. So how do we define heat energy? How do we define the heat energy? It is a form of energy that is possessed by its temperature, we can say, right? or you can also say that like it is a form of energy which gets transmitted from one body to another body because of the temperature difference. Clear? Because of the temperature difference. Or you could even say that uh, it is the energy actually possessed by all the molecules by because of its kinetic energy. You know that in each and every mass, molecules are not static, right? Even if you take the solid molecules in the solid particle are actually vibrating about their mean positions, right? So that is because of the temperature which is there, which they are possessing. Getting the point, right? So which means that vibrational kinetic energy itself, you actually call it as the heat energy of that particular body. Understood? Right? Then what are the other energies that we have? Potential energy, right? So potential energy is something, it is by virtue of its position. By virtue of its position. That means like we have different kinds of fields. Like we have fundamentally there are like you have electromagnetic forces and gravitational forces which exert a certain field around them, right? So, and by virtue of its like when you place an external object in that particular field, right? And if the object is experiencing that field, then it is going to uh, possess some kind of energy in that particular field. Got the point? Right. Then what are the other kinds of energies? What are the other kinds of energies we have? Nuclear energy, right? Nuclear energy. Then what else? What else? What we have this term called electromagnetic energy, right? That is possessed by the your EM waves, correct? That is possessed by the EM waves, right? And your light energy is actually a part of this electromagnetic energy. Clear? Right. So, and now coming, since we are in the mechanics part of our physics, so over here we are just limited to certain energies only, right? What are they? Kinetic energy, potential energy. That's it. You can actually put all the energies under this category, right? So you can put gravitational potential energy and spring potential energy both under the potential energy only, right? And what else do you have? What else do we have? That's it. There are nothing to play over here, right? So even if you write like, yeah, whether you go for the work energy theorem or modified work energy theorem, right? Or what do you say this? The principle of virtual work, right? Everywhere we are just going to play with the this potential and kinetic energies over here. Understood? So we started with the kinematics where it describes the motion. Then we entered into the Newton's laws of motion where we discussed about the cause of the motion, where that means like we are going to look at the how the forces are actually giving certain accelerations and velocities. Clear? So now, but then this is another approach. Over here also you'll again see that spring block problems and pulley weight this, what is this called, your wedge block problems, all those things, right? But then over here we are going to deal them in a different approach. Clear? See, when force is variable, when force is like constantly varying with time, then you can't directly apply certain you can't do the analysis and calculate what is its final velocity after some time or something like that, right? Rather, it is better that we go for the energy approach if force is constantly varying and you are not able to what to say, you're not able to get uh, how exactly it is varying. That means we don't have any equation which defines how force is varying here, right? You can just understand that okay, force is varying in some both in magnitude as well as in direction, but you don't have an idea how to define that variation in a equation form, right? So then it is better that instead of doing the solving the same question in the force approach, so we go for the energy approach. Got the point? Right. Okay. First, Then come to the work here. So what is work done here? So when I say work done, I'm talking about not the work done by me or you. It is work done by a force. Clear? Work done by a force. So mathematically, we define this as the integral F bar dot ds bar. Clear? Integral F bar dot ds bar. Only this much you need to just know about the work done here. Then actually from this definition of the work only, we actually define two types of the forces. What are they? Conservative and non-conservative forces, right? So let us take the discussion over here also, here only. So we have conservative and non-conservative forces. Before that, I just want to give you one point here. What is the work done by normal reaction in any case? Zero only. No, sometimes it is non-zero also. Sometimes it is non-zero also. Let us say if there is some kind of like a lift available here and block is present on this and you are like accelerating it upwards, right? So now in such a case here, on the block you have a normal reaction and the block is actually getting displaced, right? So over here, here work done by normal reaction is like non-zero. But let us say that you take any particular surface, right? Any particular surface over here, and an object is like moving on that surface. Okay, object is moving on that surface. Then in that case here, you can see that at any instant, velocity is actually tangential to this particular surface, and your normal reaction is perpendicular to this one, right? And in such cases, your work done by normal reaction is equal to 0. Understood? Right? Yes. Then now come to the conservative and non-conservative forces. So I'm going to define this conservative force over here as if work done by any force is path independent. Okay, is path independent. That means it should just depend upon your initial point and the final point, right? It should just depend on the initial point and final point. Then such a force you call it as the conservative force, right? And is path dependent. So then force is conservative, right? So it should depend only on initial and final points. Here, initial and final points. Then come to the non-conservative forces here. So non-conservative forces, which means it is path dependent, right? So work done by a non-conservative force is path dependent. Here, path dependent. Any examples for the conservative force? What is that? Spring force. Okay. Then gravitational force, right? Tension, right? Your electric force is also a conservative force only. Clear? Conservative force. Then how about work done by What about the non-conservative forces? Okay, friction, then friction, then what is that? Nuclear forces. What are those nuclear forces? Okay, where do you experience them? Mm-hmm. No, no, say. Speak out. ఎక్కడ చదివావా? No. Okay, then what else? What else? Viscous force. In fluid mechanics, we study the surface tension viscosity, right? So your viscous force is also yeah, air drag, correct, right? Your friction, viscous force, air drag, all these are the, in fact, your air drag is one of the friction viscous force only. Viscous force is also friction only. Right. Okay, got it. Now, right, agreed with this over here. Now, tell me what is the relation between work done and energy over here? You know what is the energy of a body, right? And I also have defined work done over here, right? I said like if a force is acting on a body and if it displaces the body in the direction of the force, then we define the work done over here as mathematically integral f bar dot ds bar, right? So now, what is the relation between this work done and energy here? What is that? Okay, let us say, okay, I'll ask you in another simpler terms. Let us assume that I'm applying some force on this body. Okay, this is, let us say this is resting on the smooth surface, right? Here mu is equal to 0 over here. Okay, so now, is the force doing the work on this one or not? Yes, agreed. It is doing work on this body. Now, what is happening to the energy of the body? What is happening to the energy of the body here? Huh? Okay, changing. Changing means what? Like, be precise. Increasing or decreasing? Huh? If I am applying force, it is going to accelerate. If it is accelerating, that means its velocity will increase. If its velocity will increase, then what about its kinetic energy? Increases. Understood the point? Right? Which means work done is actually a method of transferring energy to the body. Work done is a method of transferring a mechanical energy to a body. Understood? Or you can even extract the energy from the body using the work done. Clear? Right? And force is just an agent which is like which is going to help over here either to provide the energy or to remove the energy. Understood the point? Right? So, so did you understand like why we are studying this work done and energy together over here? Right? So what is work done now? What is work done now? It is actually it is a way to transfer energy to the body or from the body. Understood now? Work done is a way to transfer energy either to the body or from the body. Clear? Right. Now, I'll come to the power later. Now let us see. Look at the your work energy theorem. So, what is your work energy theorem? At least statement you should be knowing. What is that? Work done by all forces. All forces means what does it all include? conservative forces? Now, doubtful. Are these non-conservative included or not included? Right. Change in kinetic is equal to? No, complete చేయండి స్టార్ట్ చేశాను right. So what work energy theorem says is that, okay, look over here on this one only. Look at on this diagram only. Assume that on a body here, randomly F1 bar, F2 bar, some F3 bar, F4, some forces are acting on this one. Okay, I don't know whether they are conservative or non-conservative, right? And so just now I was telling you that if a single force is acting on this one, what this is doing here? What this is doing here? So whatever a work done by this particular force, right? Let us say we'll do a small calculation over here. Assume that it has moved by some s displacement, right? Starting from 0, right? It is starting from rest here, and it has covered some s displacement. Then what will be the work done in this case here? Directly for this one, you can just write like F into S. Clear? F into S. Now tell me what is the kinetic energy this body is going to possess after traveling S distance? Don't say directly it is F into S from work energy theorem. Okay, I want actual calculation. Tell me the velocity that it is going to have over here. What will be the velocity here? V square minus U square equal to 2AS, right? And that A over here is equal to F by M. Clear? So now, or just directly write down what is V square value. So V square is equal to 2A. A is nothing but F by M into S. So just make a small rearrangement here. Bring the half to the denominator, M over here. So half M V square equal to, we are getting this as equal to F into S. What does that mean? The kinetic energy which it is going to possess over here, right? Which we got this over here as work done by the force when this only single force was acting. Correct? Now let us say instead of applying the force exactly in the displacement, instead of applying in the displacement direction, let me apply this in some random direction. This is a block available here. I'm applying the force in some particular direction here, right? Same thing. Again, it got displaced by S distance over here, right? Then, and assume that this surface is smooth, right? So now tell me what will be the velocity over here after traveling S distance. Let us say this is, you can take the angle also, theta. What will be the V square now? 2 into what will be the acceleration? F cos theta by M into S. Clear? Now again make the rearrangement here. So 1 by 2 M V square is equal to F S. What is this one? This is actually the work done by this force in this case. Clear? Now that means irrespective of the angle theta over here, you can apply the force in any direction. Clear? You can apply the force in any direction, right? So you are going to get the what do you call your kinetic energy, or this change. This is nothing but the change in kinetic energy, right? So which is equal to the work done by that particular force. Now the same should be valid even if I am applying like multiple forces over here. Getting the point or not, right? So let us say I'll apply for F1, for only when F1 is applied, force F1 is applied here, then you will get, let us say, you will get some work done WD1, right? And let us say when F2, only F2 is applied here, you will get some different work done over here. Now when net of all these forces are applied on this one, that means like F1 bar and F2 bar, F3 bar plus and so on, some Fn bar, n forces are being applied over here, right? So and you find out what is the or resultant of this one here, that is going to be a single force. Yes, that is going to be a single force, right? And which means, and when I have a single force and a displacement, your work energy theorem is valid. Please try to understand this. Even if n forces are present on the body, right? What I'm going to do? Find out the net force that is going to give me a single force, right? And you know that for single force, your work energy theorem, I have proved it. Now just go back, right? So assume that this is your resultant force that is being acted, right? What do you mean by resultant? That means it is as good as all these forces are actually acting on this body. Clear? And did I define that any of them as like a conservative or non-conservative forces? Nothing, right? So which means from here I conclude that your change in kinetic energy here, this is just equal to work done by all forces, which include both conservative as well as non-conservative. Understood the point? Clear with this? Any doubts up to this one? Done, right? So this is what we call it as the your work energy theorem. Right. And this is important, that energy stored in the spring. So energy stored in the spring. So let us say that initially I have a spring which is in its natural length over here, right? And a block of mass m is like attached to this one here, right? Let us say if I displace this slowly and give a compression of delta x into the spring over here, right? So which means if I have to displace this over here, that means I have to apply some external force on this one. Correct or not? Right? Assume that while this is like slowly displaced over here, right? If this is slowly displaced here, then let us say when the compression is some this is compression is x naught, then a spring is going to apply the k x naught force on this one, right? And assume that like if it is slowly displaced, that means it is in the equilibrium, right? It is in the equilibrium. Then your external force and this kx force should be equal. Got the point? It should be equal. So if both of them are equal over here, then let us calculate what is the work done by this external force, right? Then so you know that is equal to integral f dx over here, right? And what is that f over here? F is the external force, which is always like equal to the kx, right? I'm taking that x over here is the compression at any instant, at some instant. And with that, like if you are like further compressing by small amount of dx here, so work done will be like kx into dx, right? And from here, like integration, you will get like half k x square. Assuming that, so we are going to like initial compression is 0 and the final compression is, let us say you take it as like x naught over here. Clear with this, right? Yes. So now, which means the work done by this external force, you see here, force is acting on the body and displacement is also in the direction of the body. Force is acting on the body and displacement is also in the direction of the body. So we get work done over here as positive, right? Work done as positive. From now onwards, you keep this in mind that if work done by a force is positive, if work done by a force is positive, then that means that the object on which the force has acted, object on which force has acted, that object's energy is going to increase. If work done is positive, that means that force has actually supplied that much amount of energy to that body, right? If work done is negative, then that much amount of energy, whatever is that work done by that particular force, that much amount of energy is actually taken out from that body. Clear with this? Right. So which means you see here, work done by the sectional force, we got it as equal to half k x naught square. So which means this much amount of energy is actually, what has happened here? It is given to this particular spring here, right? It is not going into the kinetic energy of this block. Block is also present over here. It is not going into the kinetic energy of the block here because I'm slowly displacing this one, right? So whatever energy that is given to the system, that is like taken by the spring, and which is what we call it as the spring potential energy. Is that clear? Spring potential energy, which means now you can see that like even if you can even start applying the force in the like to the right direction, then what will happen? It is going to elongate from its natural length, and in that case also, even though like if you are like x naught is negative, right, still you have half k x naught square here, so which you will get always as positive here. Understood? Right? So whether compression or elongation here, so your spring is always going to gain the energy here. Clear with this? Right. Let us take some questions on the how to decide whether the force is conservative or not. What is the assignment number? Right. Look at assignment number 12. Right. Assignment number 12, this is like determining whether the given force is conservative or not. So particle is moved from 0, 0 to A under the force F is equal to 3 I cap plus 4 J cap from two paths, right? So path 1 is from OP, that is like directly OP. So from O to point P over here. Then path 2, that is OQP. So let W1 and W2 be the work done by this force in these two paths. Then, so you have to compare the W1 and W2 here. How do we do that? Let us try to do the mathematical calculation for W1 and W2, right? So how do you calculate this W1 over here? How do you calculate W1? Yeah, so that is your integral f bar dot ds bar. But now point over here is that f bar is directly given in the question, no worries, right? But how do you get a ds bar over here? They gave correct. So ds bar is nothing but that is a small displacement in this OP direction. Correct? That is just a small displacement over here in the OP direction here. Right? So now, and you know what is the inclination of this one? Correct or not? You know what is the inclination of this one? So that is equal to, with a positive x-axis here, this is making 45 degrees. So you can actually write down a ds bar over here. This is equal to a ds cos 45 I cap plus ds sin 45 j cap. Getting the point? Right? And starting from O2 is root 2a. Clear? Now, let us apply the same thing here. So, integral f bar is given to you 3i cap plus 4j cap, right? And dot with ds bar. What is ds bar? Yes, that is ds by root 2 I cap plus ds by root 2 j cap, right? Tell me the calculation here. So 1 by root 2, I think you can pull it out, correct? So 1 by root 2, you pull it out here, then so I dot with I, so you have 3 ds plus 4 ds, total it is 7 ds. So integral, this is your 7 ds, so starting from 0 to root 2a, right? So you have 7 times integral ds, nothing but that is just root 2a here. So root 2a divided by root 2, you have 7a. Clear with this? Then next come to the path OQP, right? Now, I'll tell you one more thing. See, if at all, if a particle is anywhere, if a particle is just moving in a straight line, okay, particle is moving in a straight line here, then you just take the component of the force in the displacement direction and just multiply it. You'll get the work done. Okay, so I know that this is the, let us say this is f bar, and you know the angle theta over here, right? So what is the component of the force in the displacement direction, right? And you just multiply the displacement in that direction. You will get what is the work done in that direction. Clear with this, right? So now over here, since it is like your OQ is nothing but your x-axis only, so which means component in the direction is nothing but 3i cap. Clear? 3i cap. So work done in the, that is W2 over here. So is equal to, this is 3 in the direction of OQ. What is the displacement do you have? A. Right? This is A here. So directly I am multiplying 3 into A. Understood the step here? Right? This can be applied anywhere. If force is constant and particle is moving in a straight line, just take the component of the force in the direction and multiply that component of the force with that total displacement. Understood? Right. And then now come to the, we have calculated work done from O to Q. Then now Q to P. Right? What is the component of the force in the QP direction? That is nothing but your 4j cap. Clear? So and in the QP direction, your displacement is A. So then directly multiply like 4A. Clear? So we got total 7A over here. So which means like your W1 and W2 over here are same. Understood? Right. Now look at this one. A force F is equal to x square y square I cap and x square y square j cap newtons acts on the particle, so which moves in the xy plane. Okay, which moves in the xy plane here. Now determine F is conservative or not. Determine F is conservative or not. What is the path over here? They have not mentioned any direction. Okay, I think they have given something over here. Right? Find the work done by F as it moves from the part from A to C along each of the paths. That is ABC and AC, ADC and AC. Three paths are there here, right? So this is your from one second. Right. So from A, D, C. So this is one path. Then AC is another path, and then other one is your ABC. Is the force constant over here or like varying? It is varying, right? It is varying. Okay, fine, agreed. Now let us look at the. We'll calculate it for the work done in the path of like A, B, C. So which is like work done along AB plus work done along the BC. Okay, carefully look over here. Particle, when particle is moving from A to B here, it is just traveling in a straight line, right? And what is the component of the force along this direction? What is the component of the force along this direction? X square, y square. Okay. So integral x square, y square. Agreed. What is the value of y at any point on this path? 0. Right? So which means even if you write a dx over here, right, this is going to be 0 for path AB. Understood? Right? Now let us look at the for BC path. So for BC path, what is the component of the force along BC? Again x square y square. Correct or not? Right? Again, so this is along BC path. So it is x square y square into displacement. I should write it as dy over here. Agreed? Dy. And what is the x value for any point on this path here? That is equal to a, right? So then I'll modify this one here. So this is equal to integral, in place of x I can directly write a square, this is y square dy, and where is the y varying from? At this point it is 0 to a. So this is the substitute that here. So 0 to a. So what do you get from here? This is a square into y cube by 3. So which is a cube by 3. Already have a square here. So you'll get a power of 5 divided by 3. Clear? Then let us now move to the next one. That is your work done in the ADC path. So AD plus work done in around DC. Now I think similar situation is going to come over here. What will be the work done in AD path? 0. Why it is 0? Why it is 0? Because x coordinate is 0. Just like we did over here, right? Done. Now come to the work done along the DC path here. So what is the force component along the DC? X square y square only, right? X square y square only. Then your y equal to constant over here. For any point on this along this one, your y is constant. That is equal to a. So I will write a square x square. And what is a small displacement in this direction? You can write it as just dx, right? So dx over here, and which is going from 0 to a, right? What is this equal to? Again, a power of 5 divided by 3. Clear? Then now look from point A to C, right? So from point A to C, I think your force is also in the same direction. Just observe here, your both I cap and J cap component both are equal, which means at each and at any direction, any point over here, your force is along the displacement direction only, right? So directly you can write it over here that your integral, this is your x square y square I cap plus x square y square j cap, and what is the small displacement vector in this direction over here? Can I directly write it as dx I cap plus dy j cap? Yes or no? Right? You can directly write this over here as dx I cap plus dy j cap. Clear? Dx I cap plus dy j cap. And along this path, you have one more advantage. What is that? Along this path, you have one more advantage. What is that? Are x equal to y? This is x equal to y line, right? Correct or not? This is x equal to y line. So your problem over here is going to reduce a lot. So now this means this is x power of 4 plus I cap plus x power of 4 j cap. And over here dx I cap plus dx j cap. Clear? So which means you can directly write this as 2 times of integral x power of 4 dx, right? Where x is varying from 0 to a. So you have 2 a power of 5 divided by 5. Got it now, right? So they are asking whether to determine f is conservative or not. Is it conservative? No, right? So your work done along ABC and ADC is same, but then it is not equal to the work done along the AC path. Understood now? So now we should not come to the conclusion that if work done along any two paths that is chosen is same, then don't directly say that. Right? So if work done along any two random paths you have chosen, right? You have chosen some two random paths, and coincidentally, like work done in those two paths has come equal. So can you conclude that that force is conservative? You can't conclude. Clear? You can't conclude from there. What is the difficulty over there? What is the difficulty over there? That work done in those two paths might be equal, which may not be equal in a different path, in some other third path. Got the point? Right? If work done is same along any random path you take, that means all the paths you take from that initial and final points, then you can conclude that it is a conservative force. Is that clear? Right. What are all the different energies that we are going to encounter in this mechanics problems here? One is kinetic energy, right? Another one, potential energy. Let us tell me like what are all potential energies also we have. One is the gravitational potential energy, and then also we have a spring potential energy. Anything else? That's it, right? That's it. Now, only these three, with these three components, we are going to play with your all complete work energy theorem here, right? So when I said that work done is equal to change in kinetic energy, so that work done actually includes these two also, right? What is gravitational potential energy? It is nothing but work done by that mg force only, right? And what is the spring potential energy? Work done by that spring force only. Got the point, right? So, and For some time, keep this aside here. Now, let's say that there are no non-conservative forces acting in the system. No non-conservative forces acting in the system, right? Then can I say that energy of the system is going to be constant? Or maybe I should not say constant, or I should say that total energy on the system initially is equal to total energy on the system finally, because your energy is neither, you know that it is neither created nor destroyed, right? So which means like your total energy should be conserved, right? If there is no loss of energy from the system, then total energy of the system should be conserved, right? So which means I can also say that my total energy of the system initially is also equal to the total energy of the system finally. When is this valid? When is this valid? When there are no non-conservative forces, right? Only then this is valid. Okay, what if non-conservative forces are present? Then how can we modify this equation? Total energy. So see, one thing is very clear that if non-conservative forces are there, definitely that is going to reduce the energy of the total energy of the system, right? So I can write over here that if total energy of the system is getting reduced, which means initially you have some higher energy, it is getting lowered, right? So I'll write the total energy initial minus total energy final. Over here, this is nothing but the work done by non-conservative forces. Actually, this is also your modified work energy theorem only, right? How is that? Over here, in total energy, what am I including here? I'm including kinetic energy, gravitational potential energy, and spring potential energy, right? Spring potential energy, which means I know that gravitational force and spring force both are conservative forces, right? Both are conservative forces. So whatever in the work energy theorem, what did we had? We just had like a change in kinetic energy. Change in kinetic energy is nothing but the final kinetic energy minus the initial kinetic energy, right? So this is equal to, in fact, we should be writing over here. If I write non-conservative forces, work done by non-conservative forces is always like negative. So in order to take care of that sign over here, I should put a minus sign here. Clear? Then, so final kinetic energy minus initial kinetic energy. So this includes work done by mg force. If spring is there, work done by spring, and if some non-conservative forces are there, that non-conservative force also. Clear? I just took these two terms as a potential energy onto this side and rewrote this equation, and which you will get over. Understood now? Clear with this? Right. And now when to apply work energy theorem and when to apply this total energy initially equal to total energy finally, or difference in this total energy is equal to the work done by non-conservative forces. Okay. So usually I recommend that if springs are not involved in the question, if springs are not involved in the question, then it is better that you use the work energy theorem directly. Okay. If springs are involved in the question, then you go for this way of approach. That is your total energy approach. That is your total energy initially is equal to total energy finally. If friction is absent, and if let us say friction is present, then use that particular rule. Clear with this, right? Only these two approaches are there, and using this, like, you can solve any question. Understood, right? Then coming to the definition of the power, last one term is there. How do we define power? How do we define power? Can I say it as a rate of work done? Okay, rate of work done, or rate of transfer of energy. Rate of transfer of energy, both are one and the same, right? So now rate of work done over here. Let us say if you take this particular definition, so I can write this as equal to dW divided by dt, right? dW by dt. So which is nothing but, you know, dW. What is dW? F bar dot ds bar divided by dt here, right? And what is this ds bar by dt? Yes. So which is your F bar dot V bar. Clear with this, right? So mathematically, power also can be calculated using this particular formula. Clear with this, right? There was one question. Assume that there is a block that is attached to a movable pulley here, and a string is like moving or is passing over this pulley, which is a massless and frictionless pulley here. And I'm applying a force on this point of the pulley here, right? Let us say mass of this one is some m here, right? And it is given that this force is equal to 2t square. Force is a function of time, which is equal to 2t square here. Now I need power developed by force at t is equal to 6 seconds. Understood the question? Assume that there is no friction anywhere, and we need to calculate this power developed by this particular force over here, right? Now, is the force acting directly on the body? No. Okay. Will there be any power that is developed by the force over here? Will there be any force that is the force doing work over here? Is the force doing work over here? Yes or no? Yes. Why? It is not acting on the body, no? It is causing displacement. Clear? It is not required that always your force acts on some block or some wedge, something like that, right? So indirectly this force is acting on this one, right, through the mechanism of this pulley and string, right? Just look at is that particular force causing the displacement in the system or not? Understood, right? So now let us calculate the power here. How did we define the power? This is equal to F bar dot V bar. Fine. For F I directly have the expression here, 2t square. But how do you get the V here? How can you calculate velocity of this point? Acceleration. Okay. Can you calculate acceleration of this point? Can you calculate acceleration of this point? How? Constant relation, right? See that what will be the tension in this string here? That should be equal to F only applied force, right? And if you write the free body diagram for the pulley, right, what will be the tension on this one? 2t. Correct or not? 2t, right? Then what will be the, so on this block The tension force acted over here is 2T, right? So what will be the acceleration of the block here? Is the acceleration of the block is 2T upon m. Clear? 2T upon m. Then, if block is moving with an acceleration of a, then what will be the acceleration of this point? Newton's laws of motion is done. You are still saying a by 2 here. Okay, if it is not a by 2, 2a. Huh? 2a is correct answer, but then were you able to see why it is 2a? Remember, I told you this thing that if pulley is moving, right, and one side of the pulley, like the string over here, is fixed, right? If let us say if I displace the pulley over here by x amount, x length of the string here and x length of the string here gets slackened, right? It gets slackened, and where should that 2x length go? The 2x length should appear over here. Here, which means this point here, this point over here is going to move by 2x, right? Which means if the pulley which is directly connected to this mass here, so if mass moves by with an acceleration of a, then this point is going to move with an acceleration of 2a. Understood now? Right. Right. We got the acceleration of this particular point. How much is that? Acceleration of the point is equal to 2 times of the acceleration of the block here. So this is what is the acceleration of the block? 2t divided by m. So which you are getting is equal to 4t divided by m, and t is equal to this applied force F only, right? So which is equal to 4 times this is 2t square divided by m. Clear? You got the acceleration of the point. Now, how to get the velocity over here? So I need the velocity of the point at t is equal to 6 seconds. How to get that one? Shall I directly write v equal to at, u plus at? So we need to integrate. Assume that this is starting from rest here. So this is integral a dt. So a of the point over here, this is equal to 8t square divided by m into dt. Take the mass of this block as 2 kg. Okay. So then this is going to be integral 4t square dt from 0 to 6, right? So which you will get this as equal to 36 divided by 3. T square only, no? Sorry, 216, right? T cube. T cube by 3, right? That is 6 cube. 6 cube is 216. Right. So what is this equal to? Huh? 72. 72 times 4 to 88. Right. So 288 meter per second is the velocity of this particular object. Right. Directly substitute over here. So this is here 2t square. Substitute t is equal to 6 over here and multiply with the velocity which is 288. Clear? So I think you can take care of the calculation. Understood now? Right? Yes. Any doubts? Clear? Okay. Assignment number 17. So these are the questions based on the work energy theorem for a single particle. Right? So person A of 50 kg, look at the first question. Person A of 50 kg rests on the swing of length 1 meter, making an angle 37 degrees with the vertical. So another person B pushes him to swing onto the other side at 53 degrees with the vertical. So the work done by person B is, how do you calculate this? Did you understand the question here? Did you understand the question here? person A of mass like 50 kg rests on the swing of length 1 meter, right? And he's making an angle of 37 degrees over there, right? And then with vertical, so another person B pushes him to swing on to the other side at, sorry. So assume that like here, I'm just giving the side profile of the swing here. So initially it is at 37 degrees. Sorry. So then, so it was pushed from here so that it goes to 53 degrees with the vertical, right? And they're asking like what is the work done by this person over here. So how do you calculate that? How to calculate that? mg 1 minus cos theta. What is it? 1 minus cos theta. Hmm? So mg into 1 minus cos theta, that will give you this particular one. Just apply the work energy theorem, simple work energy theorem here, right? What is kinetic energy over here? 0, right? And at the extreme position, again like his kinetic energy will be 0 only, right? 0 only. Now, so there is work done by this particular force over here, which is actually like 37 degrees in the sense. What will be this? This is 1 meter given to you. So can you tell me like what is this particular height here from this ceiling over here? So he is at how much height? So 1 cos 37, right? So which is nothing but here 4 by 5 meter, right? And then this is 1 cos 53, right? So which is equal to, this is here 3 by 5. So now what is this additional height over here? 1 by 5, correct? So if this is 1 by 5 here, then which means your height of the person or has got, sorry, the level of the person has got increased over here, which means your potential energy or gravitational potential energy is going to increase over here. I mean like you have to define the reference over here. So I'm going to define this initial level itself as the reference for the potential energy. Clear? So then his potential energy over here has actually increased. So you can directly write over here. So work done is equal to, work done by this person is equal to, this is mg into 1 by 5. So what is mg here? G value? So which you will get this as equal to 100 joules. Clear? This person, the force applied by this person. Gravitational force, that is this one. Person. Actually, what happens over here is that if you apply the kinetic this work energy theorem, so work done by this person, right? Let us say I'll write this as work done by WdP plus work done by your gravitational force. All this is equal to the change in kinetic energy, right? And what is change in kinetic energy here? 0, right? So your work done by the person is actually equal to the negative of the work done by the gravity, right? So now your gravitational force is acting in the downward direction, but your displacement is in the upward direction. So you will get this as equal to minus mg into that displacement, which is your 1 by 5 meter. So where you will get this as equal to 100. Understood, no? Right? So instead of like looking at this as the work done by gravity, I showed this as a potential energy, right? Usually your gravitational potential energy is negative, right? So over here also we should I should have written like minus over here, and again you'll get like plus only. Understood the point? Clear? Right. Right. Look at the other questions. Next question. So work done by this is assignment number 17. Is this the assignment? Huh? Right. Look at the second one. So work done in time t on a body of mass m, which is accelerated from rest with respect at a speed of rest to speed v in time t1 as a function of time is given by. So they're asking work done as a function of time. What does that mean? Is force constant over here? Is force constant over here? So work done in time t on a body of mass m, which is accelerated from rest to speed v in time t1 as a function. So we'll just assume that like this is what do you call moving with a uniform acceleration only, right? Then you get what is that acceleration here? So what is that acceleration is equal to v divided by t1, right? That is the acceleration. Now that means your force F is equal to, directly you can write mass times acceleration, which is your m v divided by t1 here. If this is the force here, then can you tell me what is the displacement at any instant of time t? At any instant of time t, ut plus half at square. Initial u is 0, right? So half a, what is a here? What is a here? That is your v by t1, half a t square. So this is the displacement at any instant of time t. Now, once we have the force and displacement here, so what is the work done up to time t? Force multiplied by your force is constant here, right? Multiplied by the displacement up to time t. I think just look for the what is the correct appropriate option here. You just have to multiply these two terms here, right? What do you get? I think v by t1 and v by t1 here is there. So m by 2 into v by t1 whole square into t square. So which option is this? Option T. Clear? Then look at the third one. So velocity time graph of a particle of mass 2 kg moving in a straight line is shown figure. So work done by all forces on the particle. Now directly apply the work energy theorem, right? Work energy theorem. So what you know that work done by all the forces is nothing but this is equal to the change in the kinetic energy. And whenever in a question change in a particular quantity is asked, you must follow the sign convention that it is always final minus the initial, not initial minus final. Clear? Whenever change in a particular quantity is asked, so final value minus the initial value, right? So final value in the sense I should take over here, right? So what is the velocity over here at 2 seconds? 0, right? So your final kinetic energy, so this is your Ke final minus Ke initial here. So final kinetic energy is 0. And what is initial kinetic energy? Half m is 2 into 20 square. So we'll get minus 400 joules, which is option B. Plus 400 is also there. You have to be careful on that. Understood now? Right. Then move to the next question. Particle moves on a rough horizontal ground with some initial velocity, say v naught. If 3/4 of its kinetic energy is lost due to friction in time t naught, then coefficient of the friction between the particle and the ground is. What is the nature of the friction that is acting here? What is the nature of the friction that is acting here? Kinetic, right? If body is moving, definitely that means it is like slipping on the ground. Music. And they said that, you see, if 3/4 of the kinetic energy is lost, then what is the kinetic energy remaining? 1/4, right? So let us say initially, so they said velocity is v naught here. So which means here half m v naught square energy is present, and it has now come to 1/4 of this value here. So that is like half m v naught square, which I will rewrite this as half m into v naught by 2 whole square, which means your velocity has actually decreased from v naught to v naught by 2, right? In how much time? T naught amount of time, right? That means, can I get what is the acceleration over here? A is equal to, this is final velocity minus initial velocity, which is minus v naught by 2 divided by time, that is t naught. So which is equal to that minus mu g actually, because here I said deceleration, right? I think you can get what is mu from here. So mu is equal to v naught divided by 2g t naught. Clear with this? Right. Look at the fifth one. Block of mass m moving with a speed v compresses a spring through a distance of x before its speed is half, right? Which means its speed has become like from v to v by 2, right? And the compression in the spring at that instant is x. Now, what is the value of the spring constant they are asking? That's it, right? So you can just apply what is the, and I told you one thing, if springs are involved in the question, which method we should go for? Total energy method, right? Now, total energy of the system you should consider here. That is, system comprises of block as well as the spring here, right? So is there any, did they talk about any friction force over here? They have not talked anything about here, right? So now let us look at the, so if friction forces are not there, that means your total energy of the system is actually constant. Clear? Initially, when it is moving with the speed v, there was no compression in the spring, right? So let me write this over here. So total energy initially is equal to total energy finally. And they also did not talk about whether the block has moved up or not, up or down here, right? Which means there is no change in the gravitational potential energy. No need to look at that, right? Only kinetic energy and the spring energy, right? So kinetic energy initially is half m v square, and spring energy initially is 0, right? Which is equal to, what is the final kinetic energy here? Velocity has become what is this called? Half. So kinetic energy will become 1/4 of this half mv square, right? And what about the spring energy? Half k x square. So just bring this term onto this side and find out what is the value of k. Clear? Right. Then look at the sixth one. A small sphere starts falling from a very large height, right? And after falling a distance of 100 meters, it attains the terminal velocity and continues to fall with this velocity, right? So work done by atmosphere during the first fall of 100 meters is. Did you get the question here? You have a small sphere here, so which is falling from a very large height, correct? So after falling for 100 meters, they said that it has acquired terminal velocity. What is the meaning of terminal velocity? After that, it is going to move with the constant velocity. Clear, right? So now they're asking what is the work done by the atmosphere during the first 100 meters. How do you get that? Work done by the atmosphere during the first 100 meters. How do you get that? Hmm? What are all the, see, when the your sphere is in the air, when your sphere is in the air, what are all the forces acting on this one? One is the mg force, okay, right, and the other force by the atmosphere, right? Atmosphere. Are there any other forces? No other forces, right? So then, if you can identify all the forces over here, then directly write down your work energy theorem. So work done by all forces is equal to the change in kinetic energy, right? So work done by your work done by gravity force plus work done by atmospheric force is equal to the change in kinetic energy here. What is work done by gravitational force here? In the gravitational force only you have the displacement, right? So directly mg into what is the displacement total? 100, right? Plus, how about this one? What are they asking in the question? They're asking like work done by the atmosphere. Just keep this term as it is. You don't have to write down like what F into 100 here, right? So this is the work done by atmospheric force. So is equal to, what is the change in kinetic energy here? What is the change in kinetic energy here? Okay, they are not asking us for the exact value here. They're just asking, is it greater than or less than or something like that, correct? So let us write down just a delta Ke over here. Now, your work done by atmospheric force is equal to the, so that change in kinetic energy minus mg into 100, right? Mg into 100. Now, look at this one. So greater than the work done for next fall of 100 meters, less than the work done for next fall of 100 meters, right? And equal to 100 mg, greater than 100 mg. Definitely these two options are incorrect, right? Because we can clearly see it over here, right? Then now either it should be greater than the work done for the next fall of 100 meters. See, in the next fall of 100 meters, is there any change in kinetic energy? No, right? There is no change in kinetic energy. And if in the next fall there is no, if there is no change in kinetic energy, then what is the work done by atmospheric force in the next 100 meters? Mg into 100 only, right? But then over here we are getting this equal to this change in kinetic energy minus mg into 100, right? Change in kinetic energy minus mg into 100 here. So how do you get it from here? Okay, at least can you tell me, is your delta Ke or delta Ke over here, is it more than mg into 100 or less than mg into 100? Huh? Less than. Why? Because work done by the atmospheric force will be negative. Clear? That will be negative. So your delta Ke over here is actually less than that mg into 100, right? So now if it is less than mg into 100, what will be the magnitude of this one here? What will be the magnitude of this one? Can I say that, let us assume that your delta Ke is equal to somewhere around 50 mg. It should be less than 100 mg. I'm just assuming it as equal to 50 mg, right? So then what will be work done you will get over here? minus 50 mg, minus 50 mg. And in the next case, when it has fallen for another 100 meters, right? There you don't have any change in kinetic energy. Clear? There we don't have any change in kinetic energy. Then work done by the atmosphere as well as work done by the gravitational force, both will be equal in magnitude. Clear? Equal in magnitude. Then in the next 100 meters, what will be the work done here? Minus 100 mg. Understood now? Minus 100 mg. So now tell me whether A is correct or B is correct over here. So work done by atmosphere during the first 100 meters is less than work done for the next 100 meters. Understood or not? Not clear? Any respond? Not understood? Okay. Let us say from this level, a sphere is dropped over here. Let us say this is the, after falling the 100 meters over here, it has acquired some terminal velocity, and I'm also looking for the next 100 meters also. Clear? Where its velocity is still the terminal velocity only. Understood? Right. Now, for this first 100 meters, what can I write over here? So, work done by your gravitational force plus work done by your atmosphere is equal to the change in kinetic energy, right? So, which is equal to your half m Vt square, right? Half m Vt square. Now, what is work done by gravity here? Work done by gravitational force here. So, that is equal to mg into 100. So, which I write this as 100 mg plus this is your work done by atmosphere here, which is equal to your half m Vt square. Agreed, right? Then, so one more point I can bring it over here is that, so since we know that work done by atmosphere is negative, I can clearly say that your half m Vt square is a value less than 100 mg. Did you understand this point or not? Clear up to here, right? Because this is negative, this value will be less than 100 mg. Clear? Now come to the next 100 meters here. So in the next 100 meters, here, how will your equation get modified here? Again, like work done by the gravitational force plus work done by the atmosphere over here is equal to change in kinetic energy, but change in kinetic energy is 0. Clear? Right? Now, what is work done by atmosphere over here? Correct or not? Right? Now, over here, if this is a positive quantity, this should be a quantity which is less than 100 mg. Correct or not? This should be a magnitude of this one should be less than. I know that this is negative. But there should be a quantity less than 100 mg. So your work done by atmosphere in the first 100 meters is actually less than 100 mg. But what did I get over here? In the next 100 meters, it is exactly equal to the 100 mg, right? So got the conclusion here. So work done by the this atmospheric force in the first 100 meters is actually less than this one. Clear? Fine. So we have 1 more hour time. I want you to complete questions from this assignment. Okay. How many questions are there total? Huh? Very good. I think it will take good amount of time. complete.